All right, let's have a look at some practical issues with the energy spectra. So when we derived these mathematical tools to analyze the spectra, there were a few assumptions that we took. And so far, all signals were continuous. And infinite, and or periodic. But that's usually not the case when you analyze it, because you need to somewhat stop measuring. You cannot infinitely measure it. So usually, the signals are discretized, so they're not. So either from your measurement, you need to sample your measurement, and or you do the simulation, and then you need to have a certain time step. So you're not simulating it continuously, you're having it discretized the signal. And it's non-periodic, of course. Most of the time, because it's stochastic. Okay, so let's have a look at the issue with the periodicity first. So in particular, the energy spectrum, when you are trying to determine the spectrum, you're assuming that the signal is periodic. That's one of the assumptions that to derive the spectrum, the Fourier coefficients. So what you can do is assume that your signal is periodic. You just say, well, I don't care, I just say my signal is periodic. So let's see what happens then. So this one is the time, this one is, for example, the velocity that you measured. And let's say the signal that you measured looks like this. Then you stop measuring over here. So this one is your measuring time frame. So we have measured the signal now for this period of time. And now you say it's just periodic, you just copy it, continue to copy it. But you see, it starts out over here. So if you copy it again, and it will look something like this again. Then again, and so on. And you see, here, over there, that you're always having a jump. Jump from here to here. From here to here, and from here to here, and so on. So these jumps are going to introduce a very high frequency. So you have a lot of energy on this high, or you're detecting a lot of energy on these high frequencies, because if you assume that the signal is periodic, essentially it says that from here to here it's going to jump very fast. And but that's not truly the case. It's not really happening. So you are just introducing an artifact that you're introducing this very high frequency over there. So so you have at the interfaces very high frequencies introduced. These are artifacts. They're not physical. So what you can do is the following. So you're introducing an window function. So if we start out with the signal that we had already, so send over here. You multiply that now with the following function. That's your window function over here. So this is the signal, the window function. The one that I'm using here is a so-called flat top window function. So this window function essentially goes like this. And this one is 1. So we're multiplying now this red signal with the other blue signal here with this red function. Here in the middle, it's not going to do anything. But here it's going to squeeze them, if you're multiplying it here at the beginning and end to 0, the following signal will change the following way. It's going to be 0 over here. Here's more or less undisturbed, and it's going to be 0 at the end again. So your signal becomes something like this. And now you can copy it. It's easier to copy the next one over here. And so on. Because now they are continuous here at the interfaces. Okay, of course some issues with that, because you're essentially filtering out some of the frequencies over here. So for that reason, it helps you to deal with the very high frequencies introduced at the interfaces, but it also takes away some of the information at the on that flow. So it takes care of very high frequencies. But attenuates other frequencies as well. So there are different window functions that you can use. You can also use Henning as a common one. Flat top is another one. So there are different window functions that you can use. So no window function is perfect. You need to choose the right one that deals with the problem that you have. That means attenuates the high frequency sufficiently, but keeping the rest of the signal not too high. So there's not no perfect one that I can recommend. You just need to try out what works best for the problem that you have. So the second issue is that we don't have a continuous signal, we have discretized signals. So, and that introduces some other problems. So discretized signals. So let's say if this is your continuous signal, the discretized signal size, essentially you have a constant time step here, for example, where you're recording your values over here, over here, over here, and so on. So instead of having a continuous signal, you have only a set of data, like a long list of data for each time step. So, and then you have here frequency, time step delta t, for example, from your measurement, Or it could be also your simulation that you're advancing your computational simulation from one time step to the next one. So then you're advancing it from using delta t from one time step to the next one. And then you can you get something like a discretized signal. And you see it, for example, if you are sampling now with delta t here, very small frequencies, for example, on this level, this small frequencies would not be able to detect it. So the discretized signal cannot sense frequencies below that frequency. So the discretized signal cannot sense frequencies below 1 over delta t. So if you're now using that to create your energy spectrum, for example, you have frequency, you have your energy. So somewhere over here, this one is going to be cut off. So the F max that you can get is 1 over delta t. So, but if your original signal is discretized, then your energy spectrum is also going to be discretized. So instead of having a continuous energy spectrum, you have only a set of number of values over here. And if you paid attention, you can recreate the original signal from the energy spectrum. So that means the number of points that you have here from your original signal is identical to the number of points you have here in the energy spectrum. And you can see that the step between these two signals, between two frequencies, is going to be 1 over delta t capital T now, where delta t capital is the measuring time span. So in this case, the capital T would be over this one, delta t capital. So you have the total measuring time and you have the sampling time. You can find them both back here in the energy spectrum. The F max, you're going to find here the sampling, the delta t, the lowercase case t, and the distance between two frequencies is going to be then the overall measuring time span. Okay, so these are the issues that you deal with energy, with real life with spectra, that you have discretized signals and that you have not periodic signals, and these are ways to deal with it.